Howdy, everyone. How are you this afternoon? Good. Thank you for coming to my talk. Today I'm going to be talking about a project I did on managed aquifer recharge in Harris County. This project I did as part of my position as a faculty member at Texas A&M University. But as of tomorrow, I am moving to the next stage in my career, and I'm joining Collier Consulting as a senior groundwater engineer in Round Rock. So to give you a little bit of background and to introduce my collaborators on this, this project was sponsored by the Harris County Flood Control District and Harris County Precinct 4, and mostly conducted by my students, shown here, Sahili, who just graduated with her PhD, Emily, and Anshul. Other participants over the lifetime of the project include some of my colleagues at Texas A&M, including Ron Kaiser and Zhuping Zhan, who participated in the first phase of this study, which was a feasibility study, looking at stormwater control using these methods. And so the feasibility study we did came out and said that one of the best ways to recharge water in Harris County could be through infiltration, and in particular, enhanced infiltration that would be conducted in stormwater basins. So the idea here is that we retrofit stormwater basins because they already receive a decent amount of water to them. We don't need to do anything except passively accept that. And then if we pick them correctly, site them correctly, or if we add some retrofitting, some engineering treatments to them, we might be able to increase recharge to the groundwater if we can select our sites carefully. And so this pilot study came about as part of the bond issue that Harris County had after Hurricane Harvey. So we looked at 3 different enhanced infiltration methods, ones that had been previously used and a new proprietary system that the county wanted to try out. The first one of these was infiltration trenches, so trenching and then filling with more permeable material so that water could be accepted in there and then slowly drained out. You see the picture here with a perforated pipe, but we eliminated the pipes in our system. The second was the soil amendments, which is the idea of scraping off the top layer of these soils, which are frequently pretty high in clay, and mixing them with something that might add additional storage at the surface. And the third, like I said, was a proprietary system of plastic rods that were inserted in the ground at predetermined intervals that, according to the company that markets them, changed the hydraulic gradient in the area to promote infiltration. Okay, so for those of you not familiar, we were targeting the Chico portion of the Gulf Coast Aquifer, in particularly the areas of the county where we have the Lissy Formation as opposed to the heavy clay formations that tend to be in the south. We started with a set of geotech investigations. The stormwater basins themselves all have essentially detailed geotech on them when they're constructed. And so we had that available. However, as part of the construction, the top 10 feet of the soils had been scraped away to make the basin. And so therefore we needed to do a whole nother set of geotech investigations. And of course, since this is the Gulf Coast Aquifer, we saw that really we had this sandy loam at the surface. We were pleased to see that it wasn't as clay as we thought it was. But with depth, it was interbedded with sands and clays. Okay, so we have this alternating, very characteristic of the fluvial type environments that are the deltaic type environments that were present when the aquifer was laid down. And I should note before we move on that this is the kind of thing that makes people think, oh, recharge like this in Harris County, or recharge in Harris County in general, is incredibly difficult, in addition to what is perceived as a high water table. And we'll talk about that a little bit later. So for our experimental design, we took one lobe of the pilot site. You see the large stormwater basin here. One is a retention basin while the rest is a detention basin. The difference being filled or constantly underwater or not. And we separated out 4 plots, which we then instrumented to test the relative effectiveness of each of these different methods. So 2 is the soil amendment, 3 is the trenches, 4 is the proprietary system, and 1 is our control. So you can see us installing the different enhanced infiltration methods. Here's the soil amendment, where the top is scraped off, mixed with a sand and a compost dash mulch type material. Interestingly enough, there were some paper products in the mulch too. And at one point I went out and I looked down at the ground and I could like read a segment of text. That was a little bit of a surprise. Our next treatment is the trenches. Okay, and so this shows the trench being installed, the geotech tile going down, then 2 layers of aggregate materials designed to increase the porosity in these areas, right? So the bottom one is a recycled concrete aggregate, and the top one is a natural gravel. And that recycled concrete aggregate is going to become important later when we talk about water quality, which was a surprise as well. The proprietary system, the company came out and emplaced their plastic pipes using their specialized equipment. The final thing I want to add as not necessarily one of our test plots, but part of the experimental design was the addition of this outflow control device. This is called a smart pond, also into the proprietary system. But the idea here is that we're retrofitting the basin so that it will hold water for longer. Okay, and this was, Harris County wasn't flood control district wasn't entirely on board with this idea. The current regulations there, or the current practice there, say 24 hours of detention time, and then it gets let go. And we wanted to show that maybe we could do that a little bit longer, and that we could, with this remotely controlled system, or go out there and manually operate it, that a detention time of 48, 72 hours may not be unreasonable for such a site and could really help promote infiltration. So this was, in another way, a second pilot, if you will. Okay, so this is our set of monitoring equipment. We monitored the site originally we were going to do 1 year, and it became 2. You put equipment like this out and you cause low rainfall, right? Anybody who's installed a rain gauge knows that, right? And there's our rain gauge right there. We had an all-in-one weather station so that we could know what was coming in. We could also compare this to the flood warning system. The county had a rain gauge and a stage level in the creek that fed into this basin. We had, all of this was sent to the cloud through a cellular data logger. And then the 3 main pieces of equipment to monitor the performance were these drain gauge passive capillary lysimeters, which could measure directly infiltration rates into the subsurface. I should add they have a little bit of a caveat because they do disturb the soil when you install them. So they are subject to a little bit of error. We also looked at water levels, electrical conductivity, and temperature in the groundwater under each of these test sites. And we looked at soil moisture, electrical conductivity, and temperature in the soil at a number of places around these, around the test pads. And you can see our general equipment layout here, a piezometer in the center at 150.5 feet. All of these test pads were sited at the same elevation, with the center at the same elevation. And lysimeters, these drain gauges at the other dots here. And then each of the test pads was about 100 feet by 100 feet. Well, I shouldn't say about, I should say precisely. We had that surveyed. All right, so moving on to the data. As I said before, the Enzo cycle, we're starting in our La Nina, which we're all now very familiar with. And so the first portion of this, we had very low precipitation for the Houston area. Well, I shouldn't say low for Texas, but low for Houston. And we did not get any stormwater events. And by stormwater event, what I mean is when the detention basin is inundated with water. Okay, and these inundations, we eventually had one in the second year of this study, and you can see these purple lines. The dark purple is when the basin, when these test plots are fully inundated. So they're totally underwater. The light purple is when the basins, or when the test plots were partially inundated. So the basin was getting some water, but based on where we put the test plots, which was slightly higher up, only a portion of these plots were covered. And then everything else is maybe rain events where we weren't seeing enough to even partially cover them. When we did get our inundation in May, these are some just pictures of what the plots looked like. They were all covered to at least a foot for 24 hours. And I can, let me just see. And we retained water for 72 hours after that main event. But we did have sort of a double event, right? We had this one spike here, and then immediately within the next week afterwards, we had another. So teasing that data apart is a little bit more difficult. I should note this was the first time I had to so severely waterproof equipment like that. Soil moisture sensors aren't designed to be totally underwater. Okay, so I want to talk a little bit about the processes, the different processes we saw in these test plots, and how infiltration worked differently for each of these methods. I'm going to break this down into two categories. I'm going to break it down into the system responding to rainfall directly on it. And that's distinct from the system responding to what we call the inundation event, which is when we had standing water in the basin. Okay? And what we found was that this distinction was really important when we were interpreting our data. So each of these different methods responded differently to rainfall. The trenches showed really flashy storage. They filled up very quickly. They had large storage rates, but they didn't hold water for a long time. The soil amendment had this sustained, modest storage amount. And then the proprietary system had really big spikes in storage at depth that moved through the system really quickly. You can kind of see what this looks like with the response of soil moisture to rainfall. What we did was for each rainfall event, we looked at the before and after soil moisture and saw how much that changed, by what percent. And you'll see this is on a log scale on the side, so it's even bigger of a distinction than it looks. You can see with depth, we had less of response to rainfall. That makes sense. In each category, the deeper soil moisture sensors responded less strongly than the surface sensors did, right? And this was true for all of them. In the soil amendment, we had a higher change, but it was a lot more variable. And then the one thing I want to point out here is the recycled concrete aggregate. Okay, so it showed a very distinctly different pattern than the soil next to the untouched soil next to the trenches. Interrogating these a little further, the control shows a real quick response to rain in the shallow soil, and like I said, it's dampened in the deep. This looks very much like every natural soil moisture sensor plot I've seen. They go up and they come down, and then during the summer when it gets drier, they'll come down faster and sometimes reach a plateau at the bottom. The trenches, however, would store water So the gray here is that the sensor in the recycled concrete, and the green are all the sensors in the soil between. So the trenches would store water and really release the next day, right? So they'd fill up with rainwater and then soak into the nearby soils, and we could see that sort of pattern. Whereas a soil amendment acts like a sponge at the surface, and then it would take up water immediately and then drain over time. And so you see these longer, right here, the longer down drops in the water content. And then the proprietary system would have these big spikes, right? A much larger changes. Similar on the order of what we saw in the aggregate. Now, at this point, I am going to take out the proprietary system from the rest of the discussion. Now, the reason is we saw no groundwater in this system's well, right? When we drilled the well, there was maybe some initial perched, but after construction, we never saw water in that well again. And also, we saw no infiltration measured by those drainage gauges. And we think this is because of the mechanism of action by the system, but what unfortunately it means is that we can't quantify. And truthfully, we were a little afraid of this ahead of time. We can't quantify how much it was. We can only say, yes, it did do something. And it did change the soil moisture. So in the analysis, when we're talking about this quantification of it in long-term results, we unfortunately have to leave that one out. Okay, so talking about how this worked over a long term, we've seen the soil moisture fluctuating. We really want to look at the infiltration rates from the drain gauge lysimeters. That gives us our strongest evidence for differences in these rates. But we also have some supporting evidence from the groundwater data that we collected. Okay, and so this is over the entire 2-year study period. We saw that relative to the control and the soil amendment, the trenches had the highest amount of cumulative infiltration. Okay, now this is important because if our goal is to increase groundwater sustainability or increase groundwater recharge, this is what we want. Over a year, we want the highest amount of groundwater recharge. And we thought this was a pretty good rate that we were getting, not quite double the control. The soil amendment was a little steadier and tailed off at the end a little bit because of the rainfall patterns, but it was indeed higher than the control. But what we saw was that the control was still infiltrating more than I think anybody would have said a priori for this. My hypothesis was not that the control is going to have a decent amount of infiltration. That just wasn't something we necessarily expected. We did, though, have a high degree of variability in these measurements, depending on where we measured them. So we had the one at the plot center, and in that one, we saw more from the orange here, which is the amendment, then we saw the trenches, but that was reversed on the downslope sensor and the side slope sensor. Now, groundwater fluctuations tend to indicate the same sort of behavior that we see from the lysimeters. So the trenches, we all start out a little bit on an upswing. It was getting a little bit wetter here, but after construction in January, the trenches, after the first big rain event, the groundwater table, the system elevated the groundwater table under there. What we then saw was the soil amendment control. We did see some elevation in them, but we didn't see it lasting. Then when we started to have infiltration events, remember these were in this portion, we saw even a large step change. I had to ask my student like 3 times, is that right? Is that measurement right? Yes, it is. I took it myself. But we saw large step changes when we had inundation events, right? So there was a lot of action that correlated with what we're seeing in the infiltration gauges. And even in our big event, almost all of the systems became completely saturated. Okay, so we were under the trenches, right? The water column was just essentially continuous from the surface at its peak, from the surface downward into our well. Then over time, we saw, after that event, we saw some delayed recovery. But essentially, the trenches had a slower recession curve in the groundwater table than the other systems did. And then we started seeing, again, some more inundation events here, or at least partial inundation events. Okay, the second thing we wanted to look at, too, while we had all of these wells in, water quantity isn't the only important thing here, right? I'm sure several of you have been asking yourselves, well, what did this do to the groundwater, right? Did you move contaminants down? And so we did a whole suite of your typical groundwater salts, or salts in groundwater, and metals, and anything that we thought we might find in stormwater. And we measured a large suite of those. I'm sorry I didn't put them up here. But one of the things that indicated a bit what was going on was the total dissolved solids, right? This is just a measure of the salts, or sometimes we measure this as electrical conductivity, and the two are highly related. So I think this says the most about water quality here. We, other than the salts, we didn't have any, whoops. Too early. We didn't have any detects except for one small arsenic detect in the lysimeter. Okay, and the Gulf Coast aquifer is known for having arsenic, and so we didn't think that was a big, a big concern because we weren't seeing it in the groundwater. But back to the salts. So what we did see, though, that worried us a bit was that we had this initial flush of salt from the trenches that later stabilized higher than the background levels, okay? So we thought, well, what is going on? Are we washing salts out from the surface? And you see, though, we don't have this in the soil amendment. In fact, the soil amendment is better than the control, okay? And so we wanted to interrogate that a little bit more. But one of the things that we really looked at with the trenches is the recycled concrete aggregate. So at the end of the study, we, after we had seen these data, we said, oh gosh, what's going on with the trenches? It works so well as a quantity, but what about quality? So I had a student in the lab look at some jar tests. Basically use the USGS method to do leaching potential of salts. And we were pretty sure now that recycled concrete aggregate created a big problem. And I think some of it is, just plain dissolution of the materials in it, which, you try to be environmentally friendly and then it backfires, right? But really that concrete, when it reacted with water, especially since it was freshly crushed, right, it changed the pH and essentially started leaching calcium. And I suppose there's worse things to leach, right? But still, the fact that we were seeing these distinct changes underneath it, I think really tells us we need to be very careful about how we source the materials. We did not see nearly as big a change in the gravel, but we do think there was some washing off of the gravel, some interaction with it in the recycled concrete. No long-term deterioration of anything beyond salinity. Just a few of the things we looked at were zinc, arsenic, copper, total organic carbons, and then, like I said, a whole other suite of salts. I'm getting a little low on time, so we'll cover the inundation events. Now, one of the big takeaways with this is that we actually had somewhat disappointing performance of the actual treatments relative to the control when we were underwater. Now, why is that? Well, essentially when we're looking at the data, what we see is that rainfall and partial inundation events during the winter kept the water levels high under the trenches and the amendment, okay? And performance of those remained fairly steady over time, right? However, when the control plot was finally underwater and it had a substantial amount of hydraulic head over it, that's when it started to move, right? That's when it was able to infiltrate. Okay, so here's our event, lasted 10 days. We had that double peak, right? And really the water level in the basin as measured over the plot is indicated by this dotted line there. Okay, and here's what I mean by saying the control plot had superior infiltration during the event. 30 inches, which is quite significant amount of water, as opposed to the around 2 for the other 2 plots. And you can really see this in the change of that control plot in the groundwater table. So essentially being under that hydraulic head, increased infiltration, filled up that space, okay? But because the trenches had been infiltrating all along, that space was already filled by the time the infiltration event came in. However, we did look at that longer detention times, and it really did translate to a lot more infiltration. So depending on how we count that double bump storm, we either have like a 3.7 or an 8.5 for our 24-hour detention. With the longer detention, we had 29 to 30 inches. Right? So doing that really did make it a difference for how much water we could recharge naturally. And I say naturally, but that's with the additional retrofitting of the smart pond sensor on the basin. Okay, so just some general conclusions and recommendations. There's really a trade-off here. To achieve a year-round groundwater recharge, trenches lead to the best infiltration quantity, but soil amendments can improve infiltration quality. Okay, so if what we want is groundwater recharge, these methods do work. If what we want is to improve flood control or stormwater quality, we need to do something different. We need to consider longer detention times, and we need to carefully site where we're putting our basins, or at least not destroy the natural infiltration capacity when we are constructing our basin. Right? Preserve that the sandy loams or the sand potentials rather than siting in very heavy clays. And then to protect our groundwater quality, we have to select materials very carefully, I think, which is what we saw with the recycled concrete, and really understand where we're getting those materials from.